So our next task is to try and build a link between the theory of chain homotopy in the context of chain complexes and chain maps on the one hand, and homotopy of maps between topological spaces on the other hand. And the kind of key to all this is going to be to understand the structure of the product of the unit interval with a simplex. So let's just draw a little picture of that for the case of a 2 simplex. Okay, so here's our delta 2. And we can kind of thicken this up, make a prism like so. So this is now 0, 1 cross delta 2. And we're always going to have things oriented this way, so the 0, 1 axis is going vertical. And yeah, so we've got this triangular prism here. And if we look at the boundary of the prism, we've got the top and the bottom and the sides. And the idea is we're going to split this up into 3 tetrahedra. Okay, so the tetrahedron is delta 3. Let's just draw it here. And we're going to have some maps here. They're going to be called zeta 0, zeta 1, zeta 2. These are going to be 3 maps from the tetrahedron to this prism. And they're going to just divide the prism up into 3 tetrahedra. And so the way it's going to work out, the bottom is going to be a face of one of these tetrahedra. The top's going to be a face of another tetrahedron. Each of the 3 square sides is going to be divided up into 2 triangles, each of which is a face of one of our tetrahedra. And then there's going to be some extra faces of tetrahedra that are kind of in the middle of the prism, where two of our tetrahedra kind of match against each other. So that's how it's going to work. So we're going to need to do this for a general K. We need to give formulae for these maps zeta I. And it's going to follow an obvious kind of pattern, which we can draw in this particular case here. So this is kind of like 0E0, 0E1, 0E2 here, and then above them 1E0, 1E1, 1E2. And so we're going to have tetrahedra, and our these guys here, they're going to occur as vertices of our tetrahedra. So let's just kind of recall story about linear simplices. Okay, so if I'm given, say, A0 up to AM in some Euclidean space Rn, then I could define sort of pointy bracket A0 up to AM. So this is going to be a map from the M simplex into Rn. And the way this works is it just sends remember, a point in the M simplex is a list T0 up to Tm non-negative numbers adding up to 1. And then you just take T0 A0 up to Tm AM. Okay, so that's what we mean by a linear simplex. The simplex given by this kind of simple formula here, and so kind of the point is that if you take the ith vertex in your M simplex, that's just getting sent to the vertex AM, and so the image of this is just going to be the simplex whose corners are the AMs. Okay, so that's what we mean by linear simplices, and in this case, what's the zeta naught is going to be the simplex like this. We go 0E0, then 0E1. Sorry, no, wrong way around. We go 1E0, 1E1, 1E2. Okay, so it's a tetrahedron where one vertex on the bottom here, and then the other 3 vertices on the top. Zeta 1 is going to be So notice here in our zeta 0, E0 occurs twice, kind of once on the bottom, once on the top. For zeta 1, we've got our 4 vertices, there's 0E0, 0E1, and then 1E1 and 1E2. So we kind of, E1 occurs twice, once on the bottom, once on the top, and the other ones occur only once. And similarly, your zeta 2, same kind of thing, 0E0, 0E1, 0E2, and in this case, it's the E2 that occurs twice. Okay, so here we've got 3 vertices on the bottom and just 1 vertex on the top. And so the general picture is the obvious generalization of that. Okay, so here's the general definition. We're going to define zeta I, going to go from a k plus 1 simplex to 0, 1 crossed with the k simplex. And this is going to work for I from 0 all the way up to k. And so it's like this. The vertices go, you've got vertices E0 up to EI on the bottom, EI repeated on the top, and then all the way up to EK on the top. Okay. And so there's a bunch of maps from delta k plus 1 into this prism, as it were. We need to understand about what are the faces of these zeta I. So in other words, we're looking at the composites from delta k, and we're looking then at the going in by doing a face map delta j into delta k plus 1. And then we do this, and then we do the zeta I into 0, 1 cross delta k. Okay, so what could it be? Okay, so these are maps. These are maps from delta k into 0, 1 cross delta k. So we want to compare with what I'll call top. So you've got the top inclusion, which just sends x to 1 comma x, and the bottom okay, so those are things that we should certainly compare with. And then the other thing we want to compare with is also the sides. Okay, so what do I mean by the sides? Well, well, we've got 0, 1 cross delta k minus 1 going to 0, 1 cross delta k. Okay, this is the kind of identity cross delta q, say. And so these the delta q's give you the kind of faces of your delta k here, and so you multiply them by 0, 1, right? That's giving you the sides of your prism in the picture we had before. Okay, so that, but then this 0, 1 cross delta k minus 1, that's just kind of the same situation, one place down. We've got these maps, just as we had these zetas from delta k plus 1 to 0, 1 cross delta k. In the same way, we've got various zetas here, call them zeta p here, going from delta k. And so we divide up this this kind of in the case that we drew previously, this guy would be a prism, These guys are the kind of square faces of the prism, and each square face of the prism gets divided into two triangles, which are given by these maps zeta p here. Okay, so these are some maps from delta k into 0, 1 cross delta k that we might want to compare with, yeah, so we need to. We were comparing the composites zeta I composed with delta j with these kind of guys that we've drawn here. So we need to understand these composites here. Delta k, my face map delta j into our delta k plus 1, and then my zeta I over here to 0, 1 cross delta k. And there's going to be 4 different cases that we have to separate in. This is the first case we're going to consider, is when j is less than I. Okay. And in that case, we can do I want to claim that this diagram here commutes. So here I'm putting in my zeta I minus 1. Okay, so notice here I is bigger than j, which means at least so I is certainly bigger than 0, so I minus 1 is okay. And then here we're doing the identity crossed with delta j. So our claim is that zeta I composed of delta j is equal to id cross delta j composed of zeta I minus 1, i.e. the diagram commutes. Okay, so to prove this claim, I mean, of course, these are just linear simplices. Everything here is basically linear, so it's enough just to check that the vertices go to the right place. So it's enough to check that zeta I of delta j of EP is identity cross delta j of zeta I minus 1 of EP. This is for all the vertices of this simplex here, so that means P is going from 0 up to K. Okay, so so let's see what happens here. So P is less than J. Okay, then in this case, your EP here goes down this way, just to EP again. And then by your zeta I, well, so P is less than J, so it's certainly less than I, and so here you're just going to 0 EP. And then here again, across here, okay, so here P is less than J, so certainly we're a bit below the I minus 1 level, and so under this zeta, again, we're just going to 0 EP again. And then here you're doing the delta J, and the P is less than J, so that's just going like that. So that's okay. Okay, then what about if P is equal to J? So we've got our EJ here. So then, actually, do we need to? I think we can say. Actually, we can do the whole case where J less than or equal to P less than I. Okay, so in that case, we look at our EP here. Okay, so you're doing a delta J. Now delta J shifts the delta J sends the first J vertices to themselves, but then kind of shifts everything else up by 1. So this is going to EP plus 1 here. Okay, and now so P plus 1 is still less than or equal to I, and so if you think about how zeta I works, this is still giving you 0, EP minus EP plus 1. On the other hand, if you go up this way, right, then you do your zeta I minus 1. So again, P is less than or equal to I minus 1, so we're still all right. That's just going to 0 EP. and then we do the delta J on the EP, and now P is greater than or equal to J, so it gets moved. So we've got that sort of picture there. Okay. So now we need to consider about the case where P is between I and so P was going up as far as K here. Okay, so P is at least I, so it's strictly bigger than J, so it's certainly getting moved here to EP plus 1. Now, yeah, so now P is at least I, so P plus 1 is strictly bigger than I. So that means that we've kind of moved up to the 1. But if you think about how the zeta I works, because the EI gets repeated, this gets shifted back by 1, so this becomes 1 EP. Whereas, and here again we do the zeta I minus 1 to our EP, so again P is strictly bigger than I minus 1, so we're going up onto the top here, and then because because, like I say, because of the fact that when we do the zeta I minus 1, EI minus 1 gets repeated, so the indices get shifted left by 1. This is kind of 1 EP minus 1 under that zeta. But then you do the delta J, and J is J is going to be less than P minus 1, or J less than or equal to P minus 1, and so the EP minus 1 gets shifted by the delta J, and we go down to there. So we see that in all cases the vertices of delta K get moved the same way by the two ways around this diagram, and you see that the diagram commutes. So that deals with the case where J is strictly less than I. Okay, so now for the next case we're going to consider is where J is at least I plus 2. So notice we kind of skipped a couple of things here. Okay, the last case was for J less than I, and now we've skipped over J equals I and J equals I plus 1, which we're going to consider separately later. Now we've jumped over to J greater than or equal to I plus 2. Okay, and I left most of this diagram in place because it's kind of similar. But what happens here is we now have a zeta I here and a identity cross delta J minus 1. And so again, the claim is this commutes. And the proof is kind of very similar to the last case. I think I'm not going to go through the details. They're in the notes. But let's just note, though, what is this telling us? Here, remind you again, if we think back to the case K equals 2, here's our prism, here's one of our tetrahedra, and we're looking, this guy is giving a face of the tetrahedron. And what do we learn from this? This is giving us one of the walls of the prism, because of the delta J here, and this is kind of one of the each wall of the prism is a square, and this guy, depending on whether I is 0 or 1, is giving you one or the other of the two triangles into which we split that square. So everything coming out of this case is stuff that's kind of on the walls of the prism, on the side walls, and that was the same for the previous case as well. And then the next cases that we're going to consider are different. Okay, so the next cases we need to consider are where I and J are essentially more or less the same. And okay, in this case is as follows. So if we do got delta K, right, and then we do our delta I here to delta K plus 1, right, and then we've got some zetas, right? We could do a zeta I, or we could do a zeta I plus 1. Okay. Yeah. So the claim is that zeta I composed with delta I is zeta I plus 1 composed with delta I. And this is supposed to be I from 1 up to k. Okay, so notice that there are some missing cases here. We haven't considered I as 0, and we haven't considered I as k plus 1. Okay. Oh, did I? Yeah, no, I think yeah, this should be I minus 1. Okay, so and so again, it's enough to check on EP from P running from 0 up to K. Okay, so let's see, suppose P is less than I. So then we get delta I of EP is EP. Zeta I of EP. Okay, so so now P is less than I, so we're not doing anything special with EP. This just goes to E0 EP, and P is also less than or equal to I minus 1. So because of that, zeta I minus 1 was also just going on the bottom. So then, what about EI? Okay. So delta I of EI is EI plus 1. Okay, and then zeta I EI plus 1. And so so now we've gone past the EI, so we're going up to the top. But because of the fact that the EI has to be repeated, that's going to be 1 comma EI. But then that's also the same as, if I've done this right, zeta I minus 1, EI plus 1. Okay, so EI plus 1, that's also past the point at which zeta I minus 1 jumps from bottom to the top. So we put in a 1 and we have to shift the index to the left. And actually this is didn't really need to separate the case of I itself specifically. Actually, that's going to work in general for P greater than or equal to I. Delta I EP is going to be EP plus 1 in this case. Zeta I EP plus 1 is going to be 1 EP, which is zeta I minus 1 of EP plus 1. Okay, so we see that these two maps are the same. Okay, so what's happening here? Okay, so this is like we've got, again, if we think about the case k equals 2, then these are triangles. This is a tetrahedron going into the prism, and we've got two different tetrahedra here, and but then these two tetrahedra, they share a face. Okay, you've got two tetrahedra in the middle of the prism, and they match across one face that's sort of in the interior of the prism. So that's what's happening with this equation here. Okay, so just the last couple of cases. So again, as always, we're looking at maps. Delta K, and then by a delta here into delta K plus 1, and a zeta into 0, 1 across delta K. And the first one is, if both of these indices are just 0, I want to claim that that's just the top map, sending EP to 1 comma EP, and then the other one is, if we do the last, so that was kind of the first face, and here we're doing the last face, the delta K plus 1 face here. and then the last of the zetas. I'm going to claim that's the bottom. So we get EP. Well, under delta 0, everything always just gets shifted to EP plus 1. And then we do zeta 0. So zeta 0 kind of that sends E0 to the bottom, but everything else gets sent to the top, and the indices get shifted left by 1. So that's 1 EP. And for B, EP, right? Well, delta K plus 1. That's the kind of thing that omits the last. Omits the last. So it puts a 0 right at the end. So that means that each of the EPs just goes to EP under delta K plus 1. And then so that means we just don't have the last we don't have the last vertex in here, so everything is going onto the bottom. This just goes to 0 EP. Okay. So let's just summarize. So we do zeta I composed of delta J is going to be identity cross delta J composed of zeta I minus 1. That's J is less than I. And it's the identity cross delta J minus 1 composed with zeta I if J is at least I plus 2. And we've got zeta I delta I is the same as zeta I minus 1 delta I. For I from 1 up to K. And then zeta naught delta naught is the top. And zeta K delta K plus 1 is the bottom. Okay, so that tells you about all the boundary faces of all the zetas. And that'll do for this video. In the next video, we'll explain how to use this to produce the chain homotopy that we need.